Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the last lecture of module 6. In the lecture today, we will be discussing about the velocity structure of upper mantle, within which we will be talking about subcrustal lithosphere, seismic low velocity zone and transition zone. While discussing about lower mantle, we will cover D double prime layer and ultra low velocity zone. The velocity structure of the upper mantle shows two major effects. First, it has the discontinuities and it also has the velocity gradients that are radially symmetric in nature. Second, it contains significant lateral heterogeneity due to the cold subducting oceanic lithosphere. When we are discussing about radial velocity structure of the upper mantle, first we are supposed to discuss about subcrustal lithosphere, where the P and S wave velocities are quite high, of around 8.1 km per second and 4.5 km per second respectively in the subcrustal lithosphere. And this subcrustal lithosphere is termed as seismic lithosphere or lid, and its thickness varies from location to location, and it approximately has zero thickness at mid-oceanic ridges and at around 200 km beneath the stable cratons. And on an average, if we talk about globally, the thickness of seismic lithosphere is around 80 to 100 km in depth. Since we are talking about the cratons, we must know that the cratons are basically the old and the stable part of the continental lithosphere, where no significant tectonic activity has happened in the past several years, and it consists of Earth's two topmost layers, the crust and the upper mantle. And there is a low velocity zone which is seismic in nature, and across the entire earth we find this low velocity zone underneath the lithosphere, and it basically coincides with the expected mechanically weak asthenosphere underlying the stronger lithosphere, and they are mechanically different since the stronger lithosphere slides over weaker asthenosphere, and you can understand that the asthenosphere is kind of fluidic in nature, and the lithosphere is solid in nature. So the solid part floats onto the asthenosphere, and they are mechanically different. It happens basically because the lithosphere is the cold outer thermal boundary layer of the solid earth. Low velocity zones, depth and the magnitude vary regionally, and it is well developed and shallow in tectonically active regions, and the deeper and the less pronounced it is underneath the stable continental region. So that at the transition zone in the upper mantle, where we see the discontinuities such as the 410 km discontinuity and 660 km discontinuities, these are basically the depth of these two discontinuities in the upper mantle, and these are marked as the transition zone. And at these transition zones, the velocity increases rapidly and hence provide the features such as the triplication in the travel time curves. So if you look at this ray path diagram of P waves through the upper mantle, then you will observe the two triplications due to these two discontinuities at a distance of around 15 degree, that is around here, and around 22 degrees, that is caused by these two discontinuities such as the 410 kilometer and the 660 kilometers discontinuities. And it is sometimes difficult to study the transition zones because the data that we use from many earthquakes for the generation of the travel time curves get amalgamated with itself, and it is sometimes very hard to find the details of the triplications in the travel time curves data. Moreover, the dt by d delta, that is the slope of the travel time curve, which hence gives the ray parameter, is used to invert the velocity so that we can find out the variations of the velocity using dt by d delta. And this dt by d delta becomes uncertain due to the scattering of the data. And there are basically some solutions to these issues. First is you can use the waveform data together with travel time curve in order to derive information of the structure of the earth. And also you can use the arrays of seismometer that are spaced closely enough and hence provide the higher resolution in order to identify arrivals corresponding to the different branches of triplication. And this is a case study for the triplication in the upper mantle that was done using an array of seismic stations in order to find the upper mantle P wave velocities under the Gulf of California spreading center. And they basically used 10 earthquake data coming from the distance of 9 degree to 40 degrees, and you can see these are the observed seismogram, and these are the synthetic seismograms generated from the model of Gulf of California. This is the model here, and that is used to basically construct these synthetic seismogram, and that fits well with the observed data. And they found two triplications at 15 degree due to 410 kilometer discontinuity and another at 22 degrees due to 610 kilometer discontinuity. And the travel time curve and the synthetic seismogram, they were basically well suited to predict the velocity structure underneath Gulf of California. And you can see there is this diagram of P delta curve. It also shows the triplication features where the ray parameter increases with distance. So these are the two features that you can observe for the triplication, and these are due to the effect of the discontinuities present in the upper mantle at 410 and the 610 kilometers. In summary, what we have learnt about the seismic lithosphere, which is a high velocity zone also named as the lid, and it is not trivial to relate this directly to the mechanical lithosphere, and both are very well developed in the oceans and has less developed in the continents. So this is the high velocity zone, or you can say the velocity increases rapidly in the lid or the seismic lithosphere, and underneath which there is this part of the asthenosphere which is hotter and mobile, and this solid part of the lithosphere, which is also termed as lid or seismic lithosphere, is floating over to this asthenosphere part. And underneath cratons, higher velocity seem to go down to around 200 to 250 kilometers depth for the lithosphere, and this is also sometimes associated with tectosphere, which is considered to be more viscous and dense due to the removal of the water. And cratons consist of highly melt depleted mantle that seems to protect the overlying crust from deformation and melting. Now let's talk about the lower mantle. Velocities in the lower mantle increase rapidly with depth for roughly 100 kilometer beneath the 660 kilometer discontinuity. So there is one discontinuity for 410 kilometer discontinuity, and there is another discontinuity 610, and underneath 610 kilometer discontinuity up to a depth of around 100 kilometer. Lower mantle comes up where the velocities increase basically very rapidly up to 100 kilometer, and thereafter the velocity increases little slowly. The rapid increase in the velocity are maybe due to the mineral transformation that continues, whereas the slow increase in the velocities implies that the mineralogy and the composition of the material are not changing significantly, but the velocity increase is still happening there. That is quite slow, but that may be predominantly due to the material being compressed by higher pressure. Weak seismic discontinuities are also observed in the lower mantle at around 900 and 1300 kilometer. That may be due to the fragmented of old subducted labs. That may be the presence of the discontinuity that is global or maybe local velocity anomalies. Now let's talk about a very special feature that is present at the very base of the mantle, just above the core mantle boundary, that is known as the D double prime layer, and it is a fascinating feature and poorly understood region. D double prime layer is present at the bottom, which is a few hundred kilometers of the mantle, was initially differentiated from the rest of the mantle because the velocity gradient with depth is lower, and this is often delineated by the location of discontinuous velocity increase, which averages about 250 kilometers just above the core mantle boundary, and this was first named for a region for lower than expected velocity. The velocity gradients are little low, but the velocity increases in this region, and the depth and the thickness of this discontinuity has certain uncertainties that was described by its thickness as 250 plus minus 250 kilometer was given by Jean Lowe's in 1990, and he said that these uncertainties are maybe due to the topographical variations or maybe the presence of mineralogy composition that is significantly having the diversified set of minerals nearby the core mantle boundary. And this discontinuity was observed using the phases such as the PDP and SDS phases, which are used to observe the velocity increase in the D double prime discontinuity. And if you will see, there these phases PDP and SDS has certain phases within it, such as the SBA and the SCD phases for SDS, and these phases are basically reflections from the D double prime layers and the refractions underneath from the D double prime layer. So basically SBA reflects off the D double prime, SCD reflects just below D double prime. These combine to make the phase called SDS, and similarly you can find PDS phase. So PDP and SDS are the arrivals that comes in between the direct P and or the S phase and the co-reflected PCP and the SCS phases. So if you look at this particular diagram here, these are the SCS phase, and you can see these are the direct S arrivals, and in between you can observe these SCD phases, and these are basically due to the D double prime layer, and this D double prime layer has been observed at many locations on CMB all around the globe, and the average depth was considered to be having the discontinuity of around 250 kilometers just above the core mantle boundary. So this discontinuity D double prime has the thickness. There are certain uncertainties that I have told you. These uncertainties as per Jean Lowe's to 1990 are maybe due to the large topographic variations over a small spatial wavelengths that focus and defocus the waves. There may be no actual discontinuity, but that complex three-dimensional velocity heterogeneities give the appearance of a discontinuity. It is possible that the increase in velocity is associated with subducted lithosphere that sank to the bottom of the mantle, and D double prime has some additional complexities. There might be a strong evidence for significant seismic anisotropy at D double prime layer. These large lateral variations at both small and large spatial wavelength occur for velocities within D double prime and for topography on the core mantle boundary. There is another zone just below, or you can say just below the D double prime layer, that is just at the core mantle boundary, which is extending for the thickness of 10 to 20 kilometers just above the core mantle boundary. That is known as the ultra low velocity zone, because the velocities are very low in comparison to the surrounding mantle at that particular location. And this region is considered to be denser than the surrounding mantle, which may be partly due to the iron from the core might have induced into this ultra low velocity zone, which makes the partial melt denser in this region. The Vp and Vs are very slow, are around 10% to 30% slower than the rest of the D double prime layer, and this ultra low velocity zone is observed with an unusual body wave phase, that is SP small dks, which is similar to SKS but travels partly as a diffracted P wave. If you look at this figure, then you can see this is the earthquake and the rays are going as S wave and then travel in the outer core as K wave and then coming out as S wave. These are the normal SKS wave. But to find the ultra low velocity zone, which are basically considered to be sensitive to the P wave velocity structure just above the core mantle boundary. So these waves are going as S and then diffract around the outer core and as P wave and then enters into the outer core as K wave and then comes out of the outer core as the S wave. So that is why this is termed as SPDKS phase. Likewise, there is another phase SKPDS, which has the diffraction from the underneath. So you can see the ray is going as S wave and traveling in the outer core as K and then having the diffraction as P and then coming out as S wave. That is your SKPDS phase. So this SKPDS phase is observed with an unusual body wave phase. So this is similar to SKS but basically travels partly as a diffracted P wave. So the summary of the entire module goes like this. The ray parameter for the spherical earth is given as P is equal to R sin I by V. The ray path, travel time and the angular distance for the spherical earth is expressed as the T as a ray parameter is integral ds by V is equal to 2, that is for two-way travel time, from the RP, that is the bottoming depth, to the depth of the hypocenter, E zeta square dr divided by r in bracket zeta square minus p square to the power under root, where zeta is equal to r by v, and the distance as a function of ray parameter is the integral over the angular distance, that is 2p integral over the bottoming depth to the depth of the hypocenter dr by r integral in bracket zeta square minus p square to the power under root. We also talked about replication for the high velocity layer. That means for the replication, the back branch meets the forward branches at 2 points on travel time and the p delta curve. And for triplication, we saw that dp by d delta is equal to infinity. And we also learnt about Harglaus-Wiechert integral, that is used for travel time inversion. And Harglaus-Wiechert integral is an approach which gives the distance travelled by a ray with ray parameter p as a function of velocity structure. So the distance as a function of ray parameter is given by 2p integral rp to r naught dr by r in bracket zeta square minus p square to the power under root. The travel time data are generated by combining data from numerous earthquakes at different epicentral distances. We also learnt about the surface reflections, that are PP and SS. Both are having the maximum time phases. If you remember, we talked about the Fermat principle. As per the Fermat principle, the travel time should be extremum, either it can be maximum or minimum. And most of the phases that we record are minimum time phases, but the surface reflections such as PP and SS are maximum time phases. For the core, the shadow zone occurs for distances between 98 degrees to 145 degrees for the P wave, and seismic energy also enters into this shadow zones via P and S wave that diffracts around core. K, for the nomenclature, denotes the passage through the outer core. Reflections of the core mantle boundary are denoted by a lowercase c, and P wave in the inner core are denoted by capital I. Similarly, for S wave, it is denoted by capital J. As I also told you, the J phases are very rare to observe because these are very weak phases and also comes very later on a seismogram. As far as the today's lecture summary is concerned, the subcrustal lithosphere is characterized by high P and S wave velocity, about 8.1 and 4.5 kilometers respectively. It is approximately 0 in depth at mid-oceanic ridges and around 200 kilometers beneath the stable cratons. As I told you, the cratons are the part of the earth which has not seen considerable amount of tectonic activity in the past several years of the history, and these are also known to be the heart of the continents. Across entire earth, there is a low velocity zone beneath the lithosphere, which is expected to be the mechanically weak asthenosphere underlying the stronger lithosphere. Velocity differences between the crust and the mantle result from their different compositions. The velocity discontinuities at 410 km and 660 km is marked as the transition zone between the upper and the lower mantles. Upper mantle travel time shows two triplications due to 410 km and 660 km discontinuities at a distance of around 15 degrees and 22 degrees. At the very bottom, that means just above the core mantle boundary of around 10 to 20 kilometers from the core mantle boundary, there is an evidence of ultra low velocity zone. We also have learnt about D double prime layer, and D double prime layer is present at the very base of the mantle, and it is considered to be a very fascinating and the poorly understood region, and it also shows the strong evidence of seismic anisotropy. So these are the references of the today's lecture, and now we will meet in the next module, that is module 7. And thank you so much. Bye bye.